In this lesson, we're going to simplify radical expressions. We're going to use the properties that we took a look at in yesterday's lesson on higher order radicals and the properties of radicals, or properties of exponents and radicals that we took a look at. We're going to utilize those to do this one task called simplifying radical expressions. The key here is we want to remove as much as possible from the radical. However, we don't want to do it at the expense of having to rely on decimal approximations. We want to keep the number exact. So let's see the process of how we would go through this using our first example here. We have the square root of 16x to the 8th. The very first property that I'm going to be using on all of these examples is the property yesterday that said if you have the product of multiple pieces underneath a root, you can split it up. So I'm going to rewrite this as the square root of 16 times the square root of x to the 8th. Because I have 16 times x to the 8th, I can split it up into two separate roots. This allows me to be able to deal with it now separately. And we can see that square root of 16 is just 4. Okay, that's simplified nicely. The 4 is no longer under the square root. Okay, but what about the square root of x to the 8th? Yesterday we saw a property that said if you have a to the n to the m, it equals a to the n times m. Okay, we're going to use this property by taking our square root of x to the 8th and taking the x to the 8th piece specifically, and I'm going to rewrite it as x to the 4th squared. So I utilized this property right here, okay, to rewrite it as 4 to the power 4 squared. 4 times 2 is back to our original 8. However, there's a reason I did that, because I know that in a square root there's a little 2 right there in the crevice of the root symbol. Okay, and I also know the property we looked at yesterday that said if you have the nth root of x to the n, it simply equals x. In other words, if the root and the exponent are the same, well, here I have a root of 2 and an exponent of 2, they're the same, that they cancel each other out. And the root goes away, and I'm just left with x to the 4th. And this 4 comes down as well. Now, the property did say, though, that if n is even, like 2, that this piece has to end up in absolute value symbols. So breaking it up and simplifying it down, we end up with a solution of 4 times the absolute value of x to the 4th. And look, there's no radical symbols left, which is what we were going for. Okay, so take a look at this next example here. We have the third root of a to the 6th and b to the 9th. I'm going to start by using that first property again, where I can split this up into the third root of a to the 6th times the third root of b to the 9th. I'm then going to use that same property again to rewrite a to the 6th and b to the 9th. Now, I want to make sure that I cancel out with a root of 3. So I'm going to rewrite a to the 6th as a squared to the 3rd. 2 times 3 is 6, so that satisfies that. But now I have a third root and a third power that will end up canceling each other out. Over here, I'm going to rewrite the b to the 9th as, you might have guessed it, b to the 3rd to the 3rd. Okay, because 3 times 3 is 9, but then also the third root is going to cancel out with one of the third powers. Okay? So this third root cancels out this third power, which leaves us with a squared. This third root cancels out that third power, which leaves us with b cubed. Now, do any of these need to end up in absolute value signs? The answer is no, because the root that we were canceling out is a third root, which is an odd root. We don't put anything in absolute value signs if we're canceling out an odd root. So our simplified version becomes a squared b to the 3rd as our final simplified term. Notice that everything is out of the square root. Now, before we move on to the third problem, I want to point something out that's happening that's going to save us a lot of time in doing these problems in the future. I want you to notice first here that you have a 2 here in the square root. 2 divided out of 8 is 4. And notice how we ended up with x to the 4th. Let's look at that here. 3 divided out of 6 is 2. We ended up with an a squared. 3 divided out of 9 is 3, and look, we ended up with a b to the 3rd. Okay? So the quick trick here that eliminates us having to even do that step is to simply take the exponent value, in this case here, that would be the 9, and divide it by the radical that it's underneath. So 9 divided by 3 is 3. That means I end up with a b to the 3rd with the radicals canceled out. Okay, so let's go ahead and see if we can apply that same principle to this next example here. So again, first thing I'm going to do is I'm going to split it up. 4th root of x to the 7th times the 4th root of y to the 12th. Good. So we want to simplify each of these pieces. Now right off the bat I see that the radicals that I'm going to be canceling out are even. They're a 4th root. So I know that whatever comes out of the radical is going to be underneath or is going to be between absolute value lines. So I'm actually not going to do the first one yet. I'm going to do the second one first. So I've got here the 4th root of y to the 12th. So taking a look at that, the 4th root of y to the 12th, let's try that quick trick really quick. 12 divided by 4 is 3. So we end up with a y to the 3rd coming out of the radical, and the radical goes away. But as we said already, it has to end up in absolute value signs. Great. Okay, so the quick trick worked there. How about here in the first term? I've got a 7 as an exponent and a 4 as a root. What is 7 divided by 4? Well, unfortunately, 4 does not go into 7 evenly. Okay, well, that doesn't mean we can't use the special trick, but it does mean that there's another step to it. So what we do is this. We ask ourselves, how many times does the root value of 4 go into 7? The answer would be 1. So x to the 1st power is what ends up popping out of the radical. And again, we put that in absolute value signs. However, when I divide 4 out of 7, I've got 3 left over. I've got a remainder of 3. That is what ends up staying inside of the radical, an x to the 3rd. And the second your exponent value is smaller than your radical value, here 3 is smaller than 4, you cannot simplify it anymore. So in this case, we couldn't take everything out of the radical. We could take some out of the radical, but we still have a little bit left in that radical. So again, what did we do? 4 divided by 7. 4 goes into 7 once with a remainder of 3. So 1 multiple of x comes out, but 3 multiples of x stay in because of the remainder of 3. So to clean this up, I'm going to rewrite it as the absolute value of x times the absolute value of y to the 3rd times the 4th root of x to the 3rd. I'm going to put the radical at the end and the absolute values at the beginning. And there's our solution. Okay. So you can see that we've got this quick trick that does those properties for us. Okay. But there's also a little bit to remember when the root doesn't go evenly into the exponent. So let's take a look at 2 more examples. Here's the next one. I've got 6 times the 3rd root of negative 512 times x to the 6th times y to the 8th times z to the 4th. Okay, again, I'm going to separate everything out. I got the 6 floating around out front. But then I'm going to do it as the 3rd root of negative 512 times the 3rd root of x to the 6th times the 3rd root of y to the 8th times the 3rd root of z to the 4th. You don't have to do this. It just helps sometimes when you need to piece things apart. So let's look at this individually. The 6 stays a 6. Okay. What about the 3rd root of 512? Let's get our calculator for that. Okay, I'm gonna guess 6. So 6 times 6 times 6, because it's a 3rd root, equals 216. Let's try 7. 7 times 7 times 7 is 343. Still a little bit too small. Let's try 8. 8 times 8 times 8 gets me to 512. So the third root of 512 is 8, but we don't have the third root of 512. We have the third root of negative 512. So it's actually going to be times a negative 8. So the third root of negative 512 is negative 8. It's okay to have negatives under radicals that are odd. Okay, now let's take a look at the third root of x to the 6th. Let's try that trick. 3 goes into 6 how many times? 3 goes into 6 how many times? Twice. So an x squared is what pops out. 2 x's, so x squared. Okay, or rather, 6 divided by 3 is 2, so 2 multiples of x, that is x squared. Okay? And nothing's left because there's no remainder. Now it doesn't need to go in absolute value sign because the root that I'm canceling out is odd. Look at this next one. Third root of y to the 8th. 3 goes into 8 twice, so I end up with y squared coming out, but it goes into it twice with a remainder of 2. That means there's 2 multiples of y that stay in there, so that's the third root of y squared. So again, 3 goes into 8 twice with a remainder of 2. So 2 multiples come out because 3 goes into 8 twice, but 2 multiples are left because there's a remainder of 2 left. And lastly, we have this z. So we ask ourselves, 3 goes into 4 how many times? Once, with a remainder of 1. So 1z, one multiple of z comes out, but then because there was a remainder of 1, one multiple of z stays underneath the radical. So now that I've gotten everything out of the radicals I can, let's go ahead and combine everything we can and rearrange things so it looks a little bit nicer. First I'm going to do the 6 times negative 8 is negative 48. And then I have x squared, y squared, and I'm going to bring the z there as well. So x squared, y squared, z. And then what's nice is both of these pieces that are under the radicals, I can put back together. So it's the third root of y squared times z. And this right here is our final answer. Final answer. Okay. Great. Let's do one more example together before we finish this up, just so we can see it done one more time. So this next example I have is 5 times the square root of 63x to the 5th, y to the 7th, d to the 8th. Again, being it's a square root, I always like to write a little 2 there so that I know that that's the second root for when I start doing canceling things out. So I'm going to rewrite this as 5 times the square root of 63 times the square root of x to the 5th times the square root of y to the 7th times the square root of d to the 8th. Great, so now we can simplify. Well, the square root of 63 is not a perfect square, but I can break it up into something that is a perfect square. I think I can break this up into root 9 and root 7. So square root of 9, square root of 7, and the square root of 9 is a perfect square. It's 3. So I've got this 5 here, and a 3, and a root 7. So that becomes 15 root 7 because the 5 times the 3 is 15. Okay. Now let's focus on the next one, the second root of x to the 5th. So how many times does 2 go into 5? It goes in twice, so I have 2 multiples of x that come out, but because the radical that I'm canceling out is a square, it's even, I have to put that in absolute value signs. Now, when 2 goes into 5 2 times, but there's a remainder of 1, so in that square root, there's still 1 multiple of x left. Now let's look at the square root of y to the 7th. 2 goes into 7 3 times. So 3 multiples of y, that's y to the 3rd, comes out in absolute value signs. The 2 goes into 7 3 times, but it does have a remainder of 1. So in that square root is 1 multiple of y left. And last but not least, we have the square root of d to the 8th. This one's nice because 2 goes evenly into 8. It goes in 4 times. So we end up with 4 multiples of d coming out, and so that's d to the 4th. Again, it's in absolute value signs. So we've simplified everything. Now we just want to write things in the correct order, or in a cleaned up order. So I'm going to start with 15. I'm not going to write root 7 because I'm going to combine it with root x and root y. I'm going to go 15 times the absolute value of x squared times the absolute value of y to the 3rd times the absolute value of d to the 4th times the square root of 7x and y. So 7xy. Here is now my final simplified version of my original radical. I pulled as much out of the radical as possible while still maintaining an exact solution. Okay, so there's 5 examples of how to go about the process of simplifying a radical. We first saw it in terms of the properties that we learned yesterday, and then we also learned